Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss type 1 and type 2 superconductors. Let's begin. On the basis of magnetic behavior of superconductors, these are classified into two categories. One is type 1 superconductors and another one is type 2 superconductors. Let me explain these two categories on the basis of some different points related to these two. For type 1 superconductors, they are called soft superconductors. Type 2 superconductors are called hard superconductors. Why type 1 are called soft and type 2 are called hard? As we say, we classify superconductors on the basis of their magnetic behaviors. If we plot a graph in between external magnetic field along x direction and magnetization along y direction. So, the graph we obtained like this, that is SC. SC is that magnetic field at which a superconducting state can be changed to its normal state, that be the superconducting state. Superconducting state. After that SC, the state we obtained is the normal state. Similarly, for type 2 superconductors, if we plot the graph in between applied magnetic field along x direction and magnetization along y direction, the graph we see like this. At that point, here is SC1 Sc, that one Hc2. You have to explain it. That type 2 superconductors is characterized by two critical fields, one is Sc1 and another one is Sc2. In case of type 1 superconductors, they strictly obey the Meissner effect. Meissner effect means at critical magnetic field, that superconducting state suddenly jumps to that of normal state. But in case of type 2 superconductors, they do not follow Meissner effect strictly. Let me explain that graph to that of type 1 superconductor. Below that Sc, below that critical field, they exhibit perfect diamagnetism. As that magnetic field Sc increased, then the magnetic field lines penetrates to that of material completely, and that specimen changes to that of normal state, as we see in case of Meissner effect. From that graph, we have below critical field Sc, they exhibit perfect diamagnetisms, which is the superconducting state. Perfect diamagnetism. As the magnetic field is increased beyond Sc, then what happened? The field penetrates to that of material. The field penetrates to that material completely. Therefore, what happened? That superconducting state changed to normal state, and the given specimen or the given material, the specimen is changed to normal state. But in case of type 2 superconductors, we explain that graph. They exhibit perfect diamagnetism up to Hc1. In that region there will be the superconducting state, and they have perfectly diamagnetism in nature. They exhibit perfect diamagnetism up to magnetic field Hc1. which is called lower critical magnetic field. Lower critical magnetic field Hc1. Between Hc1 and Hc2, that region, that is a mixed region, both superconducting as well as normal region. Between Hc1 and Hc2, the specimen is in mixed state. But above Hc2, the specimen is normal conductor. Above Hc2, the specimen is normal conductor. Okay. In case of type 1 type 1 superconductors, that graph we see at Sc, critical magnetic field, that superconducting state changes to normal state, but the process is very rapidly, or we can say abruptly. In type 1 superconductor, they abruptly means suddenly jump to normal state once the magnetic field is increased higher than Sc. Once the temperature exceeds to that of once that external magnetic field exceeds to that of critical magnetic field Sc, then suddenly that superconducting state jumps to the normal state. But in case of type 2 superconductors, that process is not abruptly. They do not abruptly jump to normal state, as magnetic field is increased. In type 2 superconductor, jumping from superconducting state to that of normal state is not abrupt one, means it is not rapidly, that is a slow process as comparison to that of type 1 superconductor. Where we use type 1 superconductors, since the value of a Sc is very low, since the value of a Sc is very low, hence they have very limited applications in technology. And for that purpose we called it is a subtype superconductor. In that of same aspect, for type 2 superconductor, because of relative large field, relatively large field is required to destroy the superconductivity they have many practical applications. They have many practical applications, and for that reason we called type 2 superconductors as hard superconductors, as they required much more field to destroy that superconducting state. And similarly for type 1 it is soft superconductor, as it required small amount of external magnetic field. Okay, we use type 2 superconductors in case of particle accelerators and fusion reactors. Also we use type 2 superconductors. Examples of type 1 superconductor as lead, tin, mercury, these are the examples. Similarly for type 2 superconductors, the examples as niobium, sternum, niobium, titanium, niobium, germanium, vanadium and gallium compound. These are the examples of hard superconductors or type 2 superconductors. Here are some basic points as differentiation in between type 1 superconductors and type 2 superconductors, soft superconductors, hard superconductors, graphical way how type 1 superconductors behave to that of external magnetic field, graphical picture in between external magnetic field to that of magnetization, same for type 2. They strictly follow the Meissner effect, they do not follow that of Meissner effect. We explain that two graphs. Abruptly jump to normal state once the magnetic field is increased to higher than that of SC, but here do not abruptly jump, do not abruptly jump. The value of SC is very low, it has relatively large field. These are the examples, and again these are the examples. So, with this useful and informative notes, let me wind up this session. Thank you.